Morning, everyone. I'm Jonathan from TBG Solutions. I've got a bit of an intro slide, tell you a little bit more about where I've come from and what TBG do. But today, I'm going to talk about abstraction, a little bit about abstraction, but more so standardization, and hopefully from the perspective of pretty much everyone in this room, so sort of a management level all the way down to a developer. So hopefully you'll be able to pick at least something from this. Even if you just start thinking about standardization or abstraction, that's sort of a win. So just out of curiosity, who in the room sort of is standardizing on hardware and or software in some shape or form? Okay, less than maybe I thought, so might be more relevant, so awesome. So I'll start off with our giants are female. I saw a few of these yesterday and thought, I haven't got one. And I knew exactly who I should pick straight away. So Pam Liversidge, bit of a Sheffield legend. I'm from Sheffield. That's where TBG is sort of based. So actually went to university in Aston University in Birmingham. So it's pretty relevant. Done a hell of a lot of different things, as you can see. OBE, worked in a number of different industries. Forging, which is massive in Sheffield, or was up until the 80s, no comment. But then, yeah, she's recently, well, I say recently, in the last few decades, set up her own company, looking at specialist metal powders for mainly medical applications. But one of the biggest things that she's done is be the first female president of the Institution of Mechanical Engineers. I'm an electrical engineer by degree, so you know, if it was the IET, might maybe a bit better, but anyway. OBE, High Sheriff of South Yorkshire, so that's essentially the Queen's representative in the county of South Yorkshire, which is pretty badass. And then the first female master cutler, which is a massive thing in Sheffield. So Sheffield history, done a lot of cutlery making, plates, things like that, so she was a master cutler. Honorary doctorates, and then University of Sheffield actually named a building, an engineering building after her, so bit of a legend. So back to me. So I work at TBG Solutions. I'm the group lead for systems engineering. I've been there about 4 years, looking after the group for just nearly 2 of those. Worked at NI as an intern, did AE and inside sales. And I've done a fair chunk of different things, whether it be mil aero or high voltage DC test systems, things like that. TBG, briefly about us, we've been going since 2001, a Gold Alliance partner. The crux of what we do is essentially automated test and measurement systems, typically in aerospace defense, but it could really be anything, door handle testers we've made, all the way to being involved in the F-35 program. So, yeah, do a bit of everything. So I'll give you an example, a large-scale AT that we've done for testing 3 aircraft components in parallel, full automated environmental chamber, pure sort of software element for underwater ROV, lots of nice custom UI elements to it as well, and then measurement systems, so using NI stuff, off-the-shelf, benchtop equipment for stress testing nacelles from wind turbines. So yeah, do a bit of everything, certainly varied, so yeah. So what we're going to really look at today is why you might want to standardize, why you might want to consider it. We'll look at sort of a couple of different ways that you might want to do it, the ways that we've done it, which I've got a disclaimer, it's not the way for everyone, but it works for us. I think that's the same with a lot of things with LabVIEW in this community. And then I'll sort of show you an example of what we've done and a bit of context as well, which I think is always good. So it's going to be me on the soapbox saying standardize for 40 minutes or so, but hopefully take something away. Like I say, as with everything in LabVIEW, there's many different ways to do things, and standardization is the same. Some people like dynamic dispatch, like myself. Some people like using Actor. Some people use DQMH. Same for like frameworks, things like that. But these work for us, and we find it's pretty scalable. So why would you want to standardize? The overused block diagram ever, but it does have comments, so they've done something right. So yeah, so a bad system, something with everything all in one VI. I've seen it before, I'm sure you all have as well, where everything is in there, your reporting, your test limits, your just everything, user management. It's not great. You want to get away from doing things like this, because it's not good. So some of the things that you might find from something like that is you fragmented all your equipment and your standardized, well, there is no standardization really. It's inefficient. Yeah, try and debug that, good luck. It's inefficient in terms of development, using it, debugging it, supporting it. It's just going to cause yourself a whole range of different just horror stories. Waste, unnecessary cost. So this is sort of coming into more like the development side. If you're reinventing the wheel for every project, like why would you do that? Why would you create a login screen for every single project when you can just do it once and then reuse it? You know, some adaptation is necessary sometimes depending on customer requirements, but typically if you start with something that's general, you know, you've got a good foundation. And redundancy is a really, really popular topic at the minute, and I know NI are really pushing sort of redundancy from like the mil-aero perspective, mainly because you've got, say, a fighter jet designed 20 years ago, test equipment designed 20 years ago, but you've got to support that for 40 years, and I don't think NI is going to support a compact DAC 90 whatever for 40 years. It's going to end of life at some point. So how do you account for that redundancy? How do you account for a straight swap of hardware item and also software as well? How do you incrementally upgrade that? So redundancy is a massive point, and hopefully you'll see sort of how we've tried to mitigate that and how you might want to think about it as well. So I've got more context of sort of why this all came about for us and me personally, but when we were looking at the situation that we were in, we looked at what a piece of automated test equipment or an automated measurement system, what are the main software components, what are the typical things that every system has. And these were the main ones that we sort of picked out. There may well be more, but these are the core ones as far as I'm concerned. So a UI, you know, that helps to be standardized, and I'll show you why and some reasons. There's some things that people don't think about with UI, which is good to know. User credentials, typically people want to make sure that an operator can't change all the passwords or do a drop table on the database. Configuring the system, how do we do that repeatably and, you know, in the same way? Test limits. So test limits are going to vary between product, which, you know, because, but the way that you approach limits and how you use them in something like Test Stand or LabVIEW, you know, what can we do with those? The actual test code itself, whether that be in LabVIEW or Test Stand or whatever language, and test reporting, what you're doing with that. So how many of these do you think we can standardize on? I would say all of them, personally, in some way, shape, or form. Even down to the test code. The test code's going to be different between units because, you know, different spec requirements, but the way that you approach writing the test code for individual units can be somewhat the same, you know. So yeah, so we'll come back to this and expand on it a little bit more. So what are some of the benefits? So we've already spoken about the fact that it's inefficient, there's waste, it's difficult to support. What are some of the benefits? So simplification. So standardizing makes things simpler. So it simplifies how you're going to plan a project, how you can cost it, how you can support it, budget forecasting, resource forecasting. If you know how many units of time it takes to make a login method or something like that, then, you know, it's much easier to spec and quote and achieve that. Procurement, that's a big one that I think gets lost. If you standardize on a go-to hardware supplier, it's a lot easier, and especially in larger companies, if that supplier is a go-to supplier on the books, you know, things like lead times maybe aren't necessarily an issue. So if you've got to get them set up on the account and 6 weeks go by, it's a 4-week project, nightmare. So if you're standardizing on a supplier, it could be NI, it could be Keysight, it could be whoever. But figuring out what are the core instruments that we like to use. Efficiency. So approaching this from a developer perspective. So if you're standardizing and you're not redoing things over and over and over, your development time is going to come down. You're reusing software components. You're reusing your hardware components, or repeat orders, the same stuff. You've got experience with it. The team's experience with using this specific PXI card. Return on investment, what we'll say is with things like this, as with all sort of going down the route of, I think Sam mentioned it yesterday with like test-driven development, there is investment up front, and that might be off-putting, but it's one of those things where you're going to thank yourself 18 months down the line where you're not endlessly doing the same thing over and over. Reduction in support overhead. So if you're standardizing on one single framework and one way of doing things, further down the line, a new person can be trained and picked up and pick up the code and hopefully resolve the problem. Just mentioned training as well. Cost savings. So yeah, again, with both of these benefits or types of benefits, you're going to reduce cost, which is going to be the main driver for any business, whether you're a one-man band or whether you're a multi-billion-dollar company. So you can reduce your equipment costs, equipment support, and like I say, staff training. Always follows this nice graph. So a bit of rewind, a bit of context. So we at TVG, obviously, been going 17 years. For the last eight or so years, up until 2017, we'd been implementing standardization and abstraction, and we got some good success from it, but it wasn't perfect. It's still not perfect now, but there were areas where we highlighted, we were still repeating software design, repeating software development. So in 2017, we really looked at driving towards some kind of standardized architecture from a developer perspective. And that really helped us in outlining, okay, this is the framework we're going to use, this is the style guide we're going to use, this is X, Y, Z every project should have. And that sort of fulfilled a good proportion of what we were doing, but there were a lot of things that we didn't think about, but fortunately, unfortunately, we were put in a position with a certain project where we had to think about these other things. So we had a new project that came in last year, and this was looking at PCB production testing for a commercial customer. And they had some ATE in inverted commas, a person on a bench. You can automate people. Chernobyl proved that. One UT had one ATE, so they had X number of products, but they also had X number of ATE as well. So there was a lot of repeat build, repeat software, but done differently. The issue is that they had over 100 different units, and it was like, right, okay, how do we make a single, it was actually two systems, but they were both the same. How do we make a single ATE test 100 different units the same way? I think this was mentioned yesterday as well. How do you do something different but the same? And that's really what drove us to look at, aside from sort of the development process, what do we do with hardware? How do we make it so that we can test a product that does X and then test a product that does X, Y, Z? So that's sort of a bit of context to where we were, and that really drove us to look at the bigger picture. So from 2017, obviously, we started off with doing some standardization stuff, and that put us in the position of really having everything that's still in yellow. So we had like a standardized UI and style guide, user credential stuff, test limits, got database things, reporting. We'd loosely got that pulled together. It really meant that we had to look at system configuration and test code, how we do templates and things like that. So that's where we were last year. So hopefully you're all using at least one of these in the room. That's why you're here. LabVIEW, TestStand, CVI, NXG, whatever. That's typically what we use. So going back to the bad system. So this is what using these elements that we've highlighted, this is what a bad system might look like. Bad naming to begin with, untitled 2, v2, realcopy.vi. Don't do that, whatever you do. But yeah, everything is in that one single VI. No events, no timing, no nothing. So what we've got to do is we've got to approach it in a way that we can break out these individual modules, and whether that be a single VI using subpanels, or whether that be separate launched applications, executables, whatever flavor suits. But really, to be honest, all those elements all boil down to having a real solid architecture, or using a framework on the back end. Even down to test code, like architecting it in the right way, being sort of pragmatic in your approach of setup, main, shutdown, and really being just logical, in my opinion. I try and approach things in the same way of like DACMX or Visa or whatever, where you start off with your setup, you've got your function, and you've got your shutdown. And I think pretty much everything in ATE development or measurement development it can follow that approach. So a couple of bits on architecture. I'm not the guru for architectures. Obviously, there's a whole range of different styles and templates and things like that to get you started. But really, a couple of quick points. It needs to be scalable. You need to reuse common features and functionality. Don't copy-paste. Use a sub-VI, please. Standards and platforms. You need to sort of define, we are going to use this. You need a user guide, a style guide. If you've not got one, write one. You will use it. Intuitive control, that's a big one. That's one of these that when we had this project, we thought, right, I'm not going to say unskilled operators, but they're not degree level engineers. They are literally coming into work, pressing the go button, scanning the serial number, and that's it. How do we make the UI intuitive that they can do what they need to do without any of the feature creep bump that maybe the test department wants? I've already mentioned style guide. Get one. You've got to make sure that everything's independent of your test functionality, whether you're making your own sequencer in LabVIEW or whether you're using test stand. Let's try and keep things modular and separate. And reusing interfaces, sort of going back to the intuitive control. If we can sort of keep to the same style, use the same sort of button styles, use the same sort of colors, layouts, fonts, text, it just, from an operator perspective, gives them a real familiarity. And familiarity between ATE. I think I mentioned that later on. So expanding that, so that operator goes in, presses the start button, scans the serial number. They might not be on that one ATE all day. They might skip between 5, 10, 15 different bits of equipment. Now, if you're working in a large company that you are the supplier of the ATE, it's a bit easier. From a partner perspective, it's difficult to sell 20, 30 different ATE to a single customer. But if you've got multiple systems, then you need multiple training requirements. If it's different software, it operates a different way. You've got to retrain them, and it's not fun for anyone. Intuitive control, if it's the same, similar to the training, if it's the same, you can train someone on one system, and it carries through to the next system. If it looks the same, they can use the other system, with little or no training. Familiarity and proficiency, that's the key thing here. And really, for me, it's just as important as standardizing the back end as a developer. Think about your customer, think about the front end, think about what they want and what they need. So this is I've got a video later on, but this is sort of our standard sort of login menu. Quite clean, user system controls, defined font laid out in a logical order. So yeah, that's sort of what we aim to carry through, and you'll see that later on. So yeah, so breaking out those modules, separating the test functionality from the architecture. This is sort of the rough sort of idea of what you might have. So you've got your sort of user control at the top level, your application control, which might be like this sort of style menu. And then you've got individual launchable, whether it be executables or separate code modules for every individual element. So configuration, actual testing, and this is a big one as well, debug interface with manual control. So we, as standard, always produce a manual control screen for the system, and that's basically every bit of I/O on a system that we can basically inject, output, monitor. It helps during development, believe me. And it means that you can sort of debug code. Obviously, you're reusing the same code in the test software that you are in the manual control screen. You're not sort of having to debug through Macs, so you'll be able to more easily sort of find the problems with your code, if you like. Obviously, you should be testing the code as well. So, sort of taking that, that's sort of how we split it out. But the relationship between hardware and software, this is where we're going to move into more of the abstraction side. So, a good architecture obviously is maintainable and scalable, but we shouldn't really be relying on a single type of hardware architecture. We shouldn't be sort of saying, well, we're going to use DACMX for everything, because DACMX doesn't do everything. You can't, you have to use a switch driver to use a switch. You can't use DACMX with Keysight equipment, for example. You need to, again, pragmatically approach how you're going to use hardware with the software, and sort of define that common hardware set. And using things like dynamic dispatch with object-oriented programming, you can quite easily mitigate obsolescence very easily, which Malcolm's presentation yesterday really showed that. So that's sort of the same approach that we take for abstraction and things. So talk a bit more about abstraction layers. So anyone using hardware abstraction layers at the minute? Yeah, good. So you can shut off for the next 5 minutes. So a HAL, or hardware abstraction layer, HAL is modularization of software components to match the hardware. So we're taking that base driver and essentially wrapping it up in something that's dynamic and can be used over and over and repeated for different hardware elements. For us, the main thing is that it allows us to have demo or simulation classes. I've got another note saying that you need to do that because typically, historically, before we had a production facility in the site where I am, the production facility was just in Glasgow, which is a long way from Sheffield, believe me. So we would have a good chunk of the project where we wouldn't have the hardware, and it's like, well, how do we test it? So we create simulation classes, and it means that we can, to within a good level of similarity, simulate the system as if it was on the bench, but it's actually hundreds of miles away. And the big thing in increasing code reuse, if you're making a general parent hardware abstraction, every bit of instrumentation that you use can reuse the same code in principle. I'll quite happily show people later on sort of the back end of what we've been doing. So why would you want to abstract? So this is a typical test executive sort of layout. If you want to really know more, these next 2 slides have got images taken from probably the best white paper, I think, ever. It's called Fundamentals of Building a Test System at Hardware and Measurement Abstraction Layers by a guy called Grant Gothin, who works at Bloomy, partner in America. I actually met Grant at NI Week, and he showed me all the code, and I was like, oh my God, this is context, amazing. So yeah, that really explains what abstraction is, and especially something I'm going to talk about in the next couple of slides, measurement abstraction, which when someone said measurement abstraction, I was like, well, why and what's the point? And this really hit home of how powerful that can be. So we've got our test executive, which is going to call our high-level code modules. That's then going to call the low-level drivers, and then they're going to interact with the physical hardware. So we've got that layered approach. So if we take an example of, we've created a test sequence. There's no abstraction here. This is a no abstraction example. We've got a sequence testing a unit. In this instance, for some reason, we've taken the MUX card and we've swapped it. We need to swap it out for a matrix, for example. What are the things that we have to do with no abstraction? So we've got to go into our, we've got to first of all change the physical hardware, which, so what? Then we've got to change the driver. I'm not going to be attending the daily huddle today. Then we've got to change the actual physical driver layer. So we're changing from a MUX driver to a matrix driver. Then we've got to change the overriding sub-VI or code module that we're calling in test stand. That's 3 changes already. Ooh. Crashed. No? Oh. Slow. Must be some reflection in the HDMI. And then what we've got to do is we've got to change the actual function call. So we might have to change some inputs on the test stand side. So we've got to change what we're feeding in, the inputs, the reference. We've got to change possibly some variable that you're using in test stand to carry the instrument references. And then you've got to change all the test sequences that have that. There's 5 steps there, but if you've got, say, that's used 100 times, that's going to be a pain in the arse. And believe me, I've done it, and it is. So fundamentally, what would an abstraction layer allow us to do? So rather than doing those 5 steps, what we can do is if we architect it in a way where we can dynamically dispatch, like Malcolm spoke about yesterday, dynamically dispatch our hardware, we can essentially have a setup like this where we've got a test interface, that might be test stand, and the debug control that are calling the driver, the abstraction layer, and then talking to the hardware. So we've got a driver here, a DMM number 1, let's call it. Then we just swap out the DMM physically, and we essentially at the same time can swap out the driver. So you might have a config file that says we're using DMM number 2 now, and then dynamically dispatch that reference. So you can basically in the code we don't really have to do steps 1 to 5. We do step 1, change the physical hardware, and we just change something at the input side as well that says we're using DMM number 2. And then your code from that will dynamically call all those corresponding modules. So you're making that one single change. So hopefully that makes sense. I've explained it well enough. Again, going back to that, have a simulation class for every hardware item. Can't stress that enough. Like, that saved me so much time and so much effort. And I think there's a real benefit to doing that, especially as well from a support perspective as well. A lot of my customers, they don't have rigs connected to the internet, so I can't remote in. If I want to debug a problem, at least I've got a fighting chance by simulating all the hardware they've got on site. It really does help. So moving on from that, sort of the next level, sort of the abstraction on steroids, if you like, is looking at measurement abstraction. So you've got that hardware abstraction, you're dynamically using object-oriented programming or dynamically selecting instruments in some way. We can actually do something called measurement abstraction, which, like I say, when I first heard about it, I was skeptical and I was like, well, what's the real reason for this and how do we do it, most importantly? And again, taken from the same white paper. So essentially, we've got our test executive at the start, at the top, and then what we've got is we've got these action step types. So this is the measurement abstraction. So we've got signal input, signal output, switching, and power. So I'll skip over this middle bit and I'll come back to it. Down here, we've got our hardware abstraction. So we've got our drivers, abstracted dynamic drivers, and then the actual instruments themselves. So how does this MAL relate to this HAL here? So that basically the interconnect is done by something called the mapping framework. That could be called by a configuration file, and I'll give you more context to that in the next slide. This could be basically called by a config file, or we do it from a database. Whatever works, really. this is what it might look like. So again, we're taking that same 5-volt measurement. So what we've got is the step that we're calling. We call one of these action steps, so the mal. So what we need to do is we're doing a signal input. So a signal input is defined as connecting something, measuring something, and then disconnecting something. In terms of the how, that's going to be the switch driver and the DMM. So the switch for switching, DMM for measuring. In the middle of that, we've got this mapping framework. So we're defining from this configuration file here that to measure the 5-volt rail, we know that we need this PXI card, this channel, this DMM card, and this configuration. That can then get spat up into this mapping framework, probably another VI, that says, right, we want to do connect parameters are pulled in, measure, and then disconnect. And then obviously we're going to be interacting dynamically with our hardware abstraction layer. So that means that if in this way, if I decide actually I want to use a different card, I can just change my configuration file, or if I want to change channel, I can just change that channel there, and it's going to use a different channel. So that I find this really powerful. And we've sort of taken this and turned it into more of a general, I guess you could call it configuration abstraction for different units, and I'll give you some ideas of what we've done with that. So we start off with ATE number 1, let's call it. ATE number 1 has got, X number of instruments inside it. But ATE number 1 can test 3 different types of product, but they don't all do the same thing or all use the same instruments. So, we've got some that use all of them, some that use not all of them. So take UUT number 1 uses a MUX, DMM, and a camera. In terms of what we do in test stand, well, test stand's on the next box, but essentially what we define for MUX 1, we configure MUX 1 for this specific unit. We say, right, we know that channel 20 is going to be 5-volt, default open. Channel 64 is going to be the 24-volt rail, default closed. Now, how we use that in test stand would be, we know that this configuration, we would get that out as like sort of like a lookup table. So the developer in test stand can say, right, I want to use MUX 1. I want to connect the 5-volt rail, so I know that I need to select channel 0 and close it. Obviously, it's channel 20 in reality, but in terms of the configuration, it's the first in the configuration. And again, later on, I can show people sort of how that implements. It looks confusing, but it's not, and it works really well. So the larger sort of application from that, maybe not the measurement abstraction, but the next slide will show that. But you might have something like this. So user control at the top again. Your main menu, your individual launchable executables, your driver layer, which has got some interaction between different modules. One thing I haven't spoken about much, your output, your data type, your test data. That's good to standardize as well, whether it be something like watts, like you've seen this morning, or whether it's something that's not CSV. Hopefully I get some kudos from James, wherever he is. But yeah, there is an example that does use CSV. But don't judge me on it, but yeah, it's an old system, that's my excuse. So things like your test data and your user data and your configurations, ideally, will be going to a database. Now, that database might be local to the system, that database might be networked. To be honest, if you don't need to use a file to store something, use a database. Well, let me rephrase that. Use a database. Like if you've got configurations, there's no need really to have a file. You're opening yourself up to a lot of headaches and pain. Yeah, if anyone wants to talk more about that, I'd quite happily discuss it. So really what that means is if we've standardized on the interfaces in the backend code, the only thing that we really need to change every time is the test software. But again, in principle, the way that we architect the test stand sequence is going to be in the same way every time. And largely, because of the way that we've got the HAL and the MAL, we're going to be reutilizing the same code modules and the same techniques if we want to measure a 5-volt rail, if you want to acquire from a scope, it's going to be familiar, it's going to be largely the same. And that's really powerful for, say, for example, on that system that I've mentioned, whereby we've delivered the system, we've delivered the first 2 types of product that we can test, for example. Say the customer wanted to do the third one, they can quite easily pick that up with some simplified training. And that's sort of a real-world use case. So where we've sort of expanded this, since GDevCon #1, actually, the presentation that Matthias gave last year on packed project libraries, I didn't know what a PPL was until that presentation, and sort of realized that we could use those to really make the whole standardization thing dynamic in terms of delivering it to our customers. So we started off initially by packaging up our driver layer in a PPL. What that means is that if a customer wants a new instrument, we can essentially send them a single file that updates their whole application without having to rebuild their whole application. Initially, we've been looking at doing it with a secure FTP server. It's all right, but my package manager came along, yes, which is great if you've got systems that are connected to the network, but 99% of the time, aerospace defense customers, the internet doesn't exist. So, but it's still a great way to package up your PPL and issue it to a customer in a way that's easy for them to install. So that's been a game changer. And what we're going to be doing in the next few months is looking at sort of taking what Matthias has done in principle in making what's known as a plug-in architecture, and essentially packaging up our individual launchable components into an individual PPL. So we can update discrete components of a larger application without affecting the rest of the application. So all this is great, but I'm a big advocate for design, and everything that I've spoken about starts with design. If you don't design, you're setting yourself up for failure. Again, like with standardization in general, you invest time at the design point, it's going to pay dividends if you have issues further down the line. You can define requirements, you can define what the code's going to do, you can define what it's meant to look like, you can get buy-off from a customer, which is massively important. You don't want a customer coming back 6 months into a project and saying, actually, I don't like that, I want that to be green rather than red. And it's like, well, you've signed off that it's going to be green, so more money, please. So some design must-haves. So typically every project that we do, we have UI design, just simple UI design, no code on the back end. Software flow, so how it works from start to shutdown, give clarity to you as a developer and also an end user. Sort of tapped onto that obviously what sort of testing we're going to be doing. This is before any code is put down, by the way. System diagram. Especially with us dealing with hardware and software in one company, we have to look at what is the hardware doing, how is it going to be laid out, and how does that relate to software. It's easy if you've got a complex system to have it, even if it's just rectangles that says oscilloscope. It's nice to have. A channel list, so all your I/O mapped to the DAC device. This is really powerful, and allows you to sort of get that out of the way, assign that, right, this signal is going to be AI0 on this card. And then abstraction, so UML diagrams, pretty much industry standard for object-oriented. Again, that allows you to define your inheritance and things like that. Again, with this, like the design stuff that we have to do typically now is the software flow. The UI is going to be the same, you just copy and paste the customer's logo onto it. Diagram is going to be slightly different, your channel list is going to be slightly different. Largely the abstraction is going to be the same unless they ask for something new or different. So I'll briefly talk about the hardware side. So the system that I was talking about where they had 100 different units, this is essentially in principle what they've got. So it's a cassette-based system, standardized on specific power supplies, 18-slot PXI. So we've already outlined, okay, we're only doing X, Y, Z at this point, but if we want to do A, B, C in 5 years' time, what do we need to do? Having the foresight to sort of understand what we need in the future. So that's sort of our go-to now, half-height rack, cassette-based system. Doesn't work for everything, especially the larger items. So I'll give you a quick, I'll probably pause this at certain points, but just to give you a quick flavor, it's at like 3 times speed, so I've had to blank out customer logo, so you'll see random white boxes everywhere, so just bear with me. So yeah, so standard login screen, everything being pulled in from database, I'm logging in, and then that main menu, the one at the top that you can't quite see, that's to launch, say, like a separate LabVIEW application. The customer logo is right above it. So yeah, so everything's individually launched from executables. So you might have a test system, but you might also have a a separate LabVIEW application that also needs to run as well. That's already running. The framework's already there. You add your code. Done. Event log, so NI's got a really good toolkit, NI Event Logger. We started using that for logging what users are doing, which has always been a massive request for aerospace defence. You'd be scared at what some operators do. Historic logs, so you can look at who's been doing what. Again, so hopefully you'll see like the interfaces are very similar. They're very intuitive. They're very basic in what they're doing. We can set up settings, so we can edit all the users, we can add users. Again, this would be the same for every ATE. Define different access levels, edit users, things like that. Setting up the results database, so setting up a UDL file, you could adapt that, you could hard code it, whatever. So local or remote database, then a local path setup, about screen if it goes wrong. So this is where an old system uses CSV, but the way it's architected, you can load results in from CSV, a database, TDMS, or whatever. So we can easily filter out results and things like that. Test limits, so we can add a unit, we can add individual test limits. This is our interface to a Microsoft SQL database. So we can easily add basically any kind of test limit or variable that you want. Graph test limits, things like that. Reorder them, do whatever you want. But again, it's all simple, intuitive, one click, things are there. There's no complex runtime menus. System configuration, this is where the big things have come in. So this is where we're using the PPL to dynamically pull in what we need. So I want to add a mixed input-output card, gives me a list of instruments we've got drivers for. I can add an alias, but if the alias doesn't exist, I have to manually enter it. We've got a 6225 set up in Max with the alias MIO1. I give it an asset ID. It's actually got the customer's name on it. Define if it's calibratable, but what it will also do is it will dynamically pull in the serial number information, the location in the slot, things like that. Now, this is all simulated in Max, so some of the serial numbers are like -1 or blank. So we've got the configuration set up. So remember we had ATE number 1. So ATE number 1 has got 3 instruments. How do we set up for individual units? So everything always has a generic configuration where we've got all the I/O broken out. So we want to configure an MIO card for voltage or current. Say voltage, we set up an individual channel. But the joy of this is that I can set up channel 0 for a 5-volt check with a 0 to 5-volt range. But I can also set up channel 0 for, say, a 0 to 15-volt range in the same configuration file. So we can really dynamically use different inputs for different things, which is really powerful, especially for like DMMs where you might have like a DC check and then an AC check, having to redo that. So you create another configuration, create a new device, for example. Then we've got manual control screen. So every instrument has a default manual control screen. So the manual control screen and stuff is built at the point of the driver. So you make it once and it works for every single card. So if it's an MIO card, a 6225, it'll work in the same way as a 6221. And see here we've got a DIO card, MIO card, got the analog inputs, again, simulated devices. And then the big one as well is the custom test stand interface. So this is actual pure test stand with a LabVIEW front end. So we can dynamically select different tests. We can set up a test type that we want to do. We can look at the actual sequence file. We can actually look at execution and debug on the fly, which is pretty good. Run a test, enter a serial number, run through, get a prompt, and that's it. So all the menu items and all the UI and what you didn't see, the back end, was all code reuse, standardization, hardware abstraction, measurement abstraction. So we can use that on a commercial PCB test system, but as we've just done, we're also using that on a end-of-line production test system for commercial aviation customer. It's the same in principle in the back end. The driver layer is the same. You know, it's really, really, really helped us in what we do. So overall, hopefully it sort of piqued your interest into standardization and sort of abstraction. The main key components are that doing those things simplifies everything, makes you more efficient, optimizes what you're doing day in, day out, and most importantly, cost saving. Cost savings, the main one, as any business owner will tell you. Quick plug, obviously, the Quick Drop podcast, as I've mentioned. If you want to get hold of me, that's my email up there. That's the email for podcast. Scan that QR code. It'll take you to the anchor page for the podcast. Just give me your sort code and PIN number, and it's great. But yeah, you can get it anywhere on Apple Podcasts, Google Podcasts, wherever. If you're interested in being on, let me know. Yeah, it's been difficult to get episodes out at the minute. Just had a baby, so, well, not me personally, but my wife has, and babies are hard work. So yeah, finding the time to do that as well as work has been difficult. So yeah, so hopefully you've enjoyed that. If you've got any questions, if you want to catch me in the breaks, things like that, obviously I'm here all day. But yeah, quite happily take any questions. Got a microphone? No time? No. That's fine. All right, come and grab me.